Presenting has started. I just need to go here. This is from my other class, so let's just delete. Okay. Okay. So rotational inertia. Rotational inertia. And I can move. I don't know, is that blocking you a little bit from your, probably a little bit? Or no, not so much? So really what we want to do is tackle this new topic. It's in your textbook. It should be titled Rotational Inertia. I don't know exactly which section it's in, but it's in that same chapter in your textbook. I think it's chapter 8. I don't know which section, again, 8.3, 8.4, I don't remember, but you could certainly find it. That's an important idea. It's a really important idea. Why? Well, and what does inertia mean at this point to us? Remember, inertia is how much resistance something provides to being accelerated. Could be to speeding up at a certain rate, or a resistance to slowing down at a certain rate. Like a Mack truck, those giant 18-wheelers, they can't slow down as quickly as a smaller car, right? They both jammed on, they're both going the same speed and slam on their brakes. I would expect the smaller car could probably slide a smaller distance, of a smaller stopping distance, I would think. I'm sure they have much more powerful brakes on those trucks, but I can't imagine enough to compensate for it so that it balances out. I would imagine that the full distance a big tractor trailer going at 60 miles an hour goes before it can finally stop would be a much larger distance because it has more inertia, right? It is more difficult to slow it down. Equivalently, it's more difficult to speed it up, which is why it takes 2 minutes when you're stuck behind a Mack truck at a light turns green. How long does it take before you're finally moving 20 miles an hour, right? Finally, they shift the second gear. You're like, all right, 30 seconds later, you look at your speedometer. People get pissed off, of course. They start driving around, because they're angry because they're going so slow. But it's really that they're accelerating so slowly, right? They're gaining speed the whole time, but that speedometer for that Mack truck is slowly increasing at a very low rate. Why? Because the force from the engine is weak. False. Force from that engine is massive. Huge amount of force coming out of those engines. Those are engines are huge and super powerful. Why does that truck speed up so slowly? It's the mass, right? Acceleration is inversely proportional to mass. This is connecting back with something you should know already, and I'm sure you do. Large mass objects, especially when they're really large, will speed up more slowly, or they'll slow down more slowly. They'll resist a change in speed, and they'll resist a change in direction. You might not even be trying to change their speed, but maybe just trying to get them to turn, physically change their direction of motion. Heavier objects will do that with more difficulty than lighter objects. The question is, again, that's the concept of inertia. The question is, how does this play out for things that are rotating? It's a similar idea. If you go over to something that's, let's say, a wheel. I might have said this to your class before, but actually I have a wheel. Where's my wheel? I have a bicycle wheel, believe it or not. So this particular wheel provides a certain resistance to being rotated. And what I really mean is a resistance to a torque. So when I try to apply a torque, sorry if your camera at home is a little crooked. Fix that. Actually, you know what? This is probably better. Yeah. That should be better. Yeah. So when you're trying to provide a torque, of course, you would be applying a force in this direction. I mean, pushing down is certainly not going to make it spin. It'll just compress the tire. I mean, or alternatively, you could glue a piece of string here and then pull upward, and it's just going to stretch the tire out. It's certainly not going to make it spin. We know that I have to push with a force that's tangent, right? And the torque, again, is how much force I'm physically providing right here where my hand contacts this wheel times the distance from here to here, right? And that product, R times F, gives me the torque provided to this wheel, which causes a rotation, which we already know that. However, if I were to tape a bunch of heavy, masses, like these big heavy pieces of metal, duct tape it here, another one, duct tape it here, duct tape it here, heck, add 15 pounds worth of metal to the edge rim of this, and then come over to it and do the same thing with my hand, would we expect that it would spin the same angle before stopping? If I did it the first experiment, no metal, like that, we count how many rotations. Second experiment, add a whole bunch of weight all the way around the edge of it, come over with your hand and try to provide the same force that you did before. Would we expect that it would get the same amount of rotations? More, less, the same, either way, why? What would you say? Yeah, less, why? It might only in fact go like this. Like, wow, that's not that much compared to before. When you take the metal off, do the same torque, wow, you got like 6 rotations out of that. So why would it be less? Exactly, it's heavier, it's more mass, absolutely, and it's resisting that motion. It's harder to get it to move in the first place, right? So you can apply the same torque to both of those wheels that I've described, the lighter one and the heavier one, and the heavier one will not accelerate as quickly. The angular acceleration, which occurs during the push, that angular acceleration only occurs during the time that the torque is being applied. That in the real world might have only been like 0.1 seconds. So you get 0.1 seconds of a torque being applied before my hand comes off, and that means you only have 0.1 seconds of an angular acceleration occurring during that 1/10 of a second. But the rate of how rapidly the speed increases during this moment depends on how much torque you get. We know that already, but it depends, again, on how heavy it is. And if it's got too much rotation, again, we call that rotational inertia, it might not rotate that, gain that much speed from that torque. Lighter things will accelerate more quickly rotationally during a torque, and heavier wheels potentially will accelerate more slowly during the torque. And I just jot that down here, rotational inertia. This is the resistance any rotating object provides. I mean, I don't know if provides, it provides it. I don't know what other word to put there. Creates, generates, I don't know. The resistance any rotating object provides while a torque is applied. More weight, or I shouldn't say more, heavier, generally speaking, I'll maybe make that comment here. Generally speaking, a heavier wheel, because later what we're going to learn about is that it's not just the weight. It also turns out that the radius of the tire actually matters. Because although I could, in terms of rotational inertia, this thing we're talking about, it's not just weight. Again, the physical width of the tire matters, because even if I could add those metal bars, like I said, all the way around this, keeping the same wheel, so I'm not changing R. So in that experiment we just talked about, I come over and apply the same torque at the same distance, R. So I'm getting the same torque. However, what if I took out a much wider wheel, still put those metal bars all the way around it, so the rotational inertia would be much more. Now I go way up there and go like this with my hand, up at the top of this big wheel with the same sideways force. Am I getting more torque by doing that? I'm actually getting more torque, right? Because now the distance from where my hand is on the top of the wheel up here, all the way down to the center of the wheel, which might be down here, the big R now. Now, even though I'm applying the same force, I'm getting more torque. So you might find that it actually can compensate for some of the extra weight it might have. So all I'm trying to point out is I'm starting with the first layer of this idea. The first layer of this idea is that weight matters. Soon we'll be recognizing that the second layer is that the physical width of the wheel, the diameter of the wheel, matters also. Generally speaking, a heavier wheel has less angular acceleration due to a torque. I know it's a lot of words, but this is the idea. Due to a torque compared to a lighter wheel. The lighter wheel would have a greater angular acceleration. Again, omega is how fast it's rotating after the torque is applied. Like this is a certain omega. After my hand comes off of this, more or less it's a constant rotational speed. Wait long enough, it surely is slowing down. But over just a second, if I go like this, over the first second, it's more or less a constant speed. It's like a bowling ball. A bowling ball on the alley, is it slowing down significantly during the time it's rolling? A little bit, but it's almost no friction there. It's a rolling effect. It's not sliding. So if the speed of the ball when it leaves your hand is 20 miles per hour, maybe the speed is 19.6 miles per hour or 19.7 miles per hour when it strikes the pins. Might have lost a little speed due to the air resistance and any frictional effects, but it's minimal. So over the first 3 meters of the ball rolling, you can say it's pretty much a constant speed during that. It hasn't lost much speed in that 3 meters. Same idea here. Again, after the torque is applied, more or less, it's a constant speed. And that rotational speed that it has, again, yes, depends on the torque, but it depends on how much rotational inertia it has. That's an idea. It's idea number one. And so I can actually make the same idea or write the same thing. Alpha is proportional to 1 over rotational inertia. So you make the connection where we're going to be building a law known as Newton's second law for rotational motion. It may or may not be surprising to you that once we see it, it looks the same. It just has different symbols representing different things, but structurally it all looks the same. The ideas are all the same. There's a symbol for rotational inertia, and it's the symbol I, capital I. I'll be writing that in a minute. So in a textbook, you'd see alpha, the angular acceleration that it experiences during the time the torque is applied, is proportional to 1 over capital I. And you'd end up having to learn that capital I is a symbol we use, well, I, inertia, for rotational inertia. I will also point out before I go to the next screen that another word for this is moment of inertia. I don't know why, to be honest. I have no idea. Somebody researches that, let me know. I never bothered. I know in a textbook, instead of saying, so a.k.a, this is an a.k.a. I can't believe I just said a.k.a. because I never say that. And it's weird that my son has been like, I listen to him on his Xbox with his headphones, and I hear him saying AKA every 5 minutes. And I was like, do you even know what that means? It means also known as, by the way. Usually you say it when you're referencing something has a different name, a different reference name. And he's using it in these ways doesn't even make sense. I'm like, is this a trend? This is a cool thing? Yeah, AKA, everything's AKA. I finally taught him what it means, and he's like, oh, here I just said AKA. I don't know. I say that probably once per year, maybe once per 2 years. But I did say it. AKA, that's another, also known as moment of inertia. Two words for the same thing in the same way where we say rotational speed. Some people say angular speed. Two names for the same thing. Again, where does the word moment of, I never understood that. I don't know, but just be aware of that. Okay. Now we're going to go into the more math part. Mathematical models for rotational inertia. So capital I, as I had suggested, is the symbol for rotational inertia. This is what we call the quantities symbol, quantity symbol, because each thing is its own quantity. A quantity is something you can measure, right? So force is a quantity, time is a quantity, mass is a quantity. You can measure it, it's a quantity. We have symbols like this is like F for force and M for mass, I for moment of inertia or rotational inertia. And I'm going to write a formula down and then I'm going to explain it so that it makes sense. And I promise you I can achieve that. Just give it a moment. This is a formula that you'll see inside your textbook, or you just Google rotational inertia and hit images. You'll probably right away see this, something that shows this formula. It might look like, what does that really mean? Which is fine, but it's actually very simple to use. It just means it's a summation, pointing out that even when we write F net equals MA, there's a lot of textbooks that write it like this. They write it as a sigma. Sigma means the summation. It's a summation symbol, sigma, Greek letter. And it means to add. So I'm just pointing out that these are two ways here of writing the same thing. And in math, you will actually see the sigma symbol a lot. Maybe by the time you're in senior year, you start seeing math teachers using that. This means you're going to add things up. This is the sum symbol. And since I haven't been so I actually, for like many years, I actually wrote it like this. And I just got the sense that some kids just did it like were confused by the symbol. So eventually I just abandoned it. I started writing F net equals MA. So since I haven't really written that symbol much this year, I'm taking the moment to tell you that's the sum symbol. And I'll draw a picture now and explain how you would apply this formula. This formula is used for calculating. So like for linear problems, they'd say, a box is sitting on a table. The box has a mass of 2 kilograms. That's the inertia. They just tell you it's 2 kilograms. And a force of 10 newtons is applied. Determine the acceleration. You don't calculate the mass. They just tell you what the mass is. Well, it turns out with this topic, you have to calculate the rotational inertia. They're not going to give it to you. It's a number, but there's a skill in just seeing, can the kid actually determine what it is? Because it depends, yes, on the weight, but also depends on where that weight is. How far away from the axis of rotation is that weight, based on what I had previously said with the big wheel versus the small wheel. This is why we have mass. Mass matters. Mass is like weight, which we said. And R is how far the mass is from rotation axis. Axis of rotation. I'm just going to put A dot R. If you want to write it all out, you can. So where is most of the mass for the wheel? Do the spokes have some mass? Yeah. I wouldn't guess that that's most of the, I wouldn't guess that they're a significant portion. I'm going to guess that if I were to remove all of these spokes and put them on a scale and then take whatever's left, which is the whole thing, minus the spokes and weigh it, that the spokes provide a very small fraction of the overall weight and mass. Most of the mass is probably in the rim. This bar is actually heavy, but cutting that off for a regular wheel, this wouldn't be here. I would imagine that most of the weight of the wheel is in the rim and in the tire. The rubber can be pretty hefty. So when we say R, that R is how far away is the mass from the center. The center, again, is here. If I'm referencing the tire and the rim as where most of the mass is, then R is just the distance from the center, the axis of rotation, which is this rod in the center, because it's all rotating around that axis, drawn straight out to where the mass is. It would just be R, which is the radius of your tire. But there's a sum symbol there, and you might say, like, how would you apply a sum symbol to the tire? And before I come back to it, I guess, before I go to the board, what you would have to do is imagine breaking the tire with a saw, like cutting with a saw here, and like go cut, and then I don't know, maybe not even cutting all the way through, just cutting enough with a saw to make a line in the rubber, and then going a few inches over and cutting, and then go a few inches over and cutting, a few inches over and cutting to make a line, and do it all the way around. what you'd be doing is visualizing the weight of the tire as segments. And you'd call one segment, one little block, because you cut with a saw, and then a few inches over, cut with a saw. You'd be like, I'm going to call that M1. Then I'm going to rotate it a little bit, and the second segment I'll call M2. And the next segment I'll call M3, and M4, and then 5. And you'd have to visualize the whole weight of the tire as segments. And that's when you would say, okay, sum means that we'd have to add up the mass of that first segment that you created like this. You'd technically, I guess, have to take it off and put it on a scale to weigh it, then put it back. So you at least know what the mass is. And then you'd multiply that mass of that little segment times how far it is from the center, M times R. And you'd write it as M1 times R1, but the R actually has to be squared. That would be the amount of inertia or resistance to rotating this wheel experience and this total resistance that one segment provides. Because each little segment provides a little extra resistance. It's like if I have a box that originally has some resistance when I'm pushing it sideways, if I add one metal bar to it, well, that one metal bar has just added some inertia to the total mass of the box plus bar now. So it's the same idea. The total resistance that the wheel provides is the sum of all of these segments. Each segment provides a little bit of resistance. So for each one, you would have to do the first little chunk times the distance from the center squared, plus, then you'd turn it a little bit to M2. You'd have to know what its mass is, the little chunk there is, times its distance, which is the same, squared, turn it, plus M3, plus R3 squared, turn it, and you literally have to do that all the way around. Then you'd add them all up. That's the idea of how the formula would play out for just your typical bicycle wheel. This is the total rotational inertia of the object, of whatever it is that's going to spin. And you would write this as M1 R1 squared plus M2 R2 squared plus M3 R3 squared plus M, and we usually would write N Rn squared, just meaning, N is technically just called an index, and it can go from 1 to 1 to infinity, I guess. Depends on how small these little sections are. I mean, technically, when I described my saw, I could have made two really close slivers, like really, really close together, so that I only move like 2 millimeters over and then do the saw, then move 2 millimeters over and do the saw. You're like, wow, by that choice, you just made like 10,000 different segments. And I'm like, well, I'd have to do 10,000 of these terms. M1 plus M2 plus M, all the way up to M1000 times R1000 squared. So my point is, N is just however many pieces you have. This is the total. This is how you apply. This whole thing is that. How would this look like? How would this look on a wheel again? Like I said, I think it's worth seeing that. You'd have to break out a little chunk and call that M1. Maybe this is M2. This is M3. I'm certainly not going to go around the whole wheel doing this. That takes too long. M4, M5. You get the idea. Here's the center. Here's what we call R1. Here's what we call R5. R5 is just the distance from the center out to M5, segment M5. And R1 is the distance from the center out to segment M1. And again, these are just numbers. M1 has a mass in kilograms. R is a distance in meters. You do it out mathematically and square the R, and then you just add it to the next one, to the next one. The next go all the way around. All the way around. So you add each segment. If that makes sense to you, then you get the idea of how this works. Because now we're going to do an example. They don't usually give, start off with wheels, but I think a wheel is a perfectly good thing to show a student so they can understand it a little bit. I'm next going to show you a more typical starting point for doing a problem. The typical one you see in a textbook, you probably see it in your textbook, will look like this. They're going to show a little blob or ball on the ends, like this. They might describe that it's a metal ball, metal ball, or metal spheres. Metal because they want them to have some weight to them. And they say that it's connected to this rod that has no weight or no mass. These are like the spokes, because that actually becomes more challenging. Let me point that out. It's simpler when all of the segments I talked about are all out at the same distance because they're all along the tire, along the rim. If you said, yeah, but you'd actually be underestimating the total rotational inertia because it does have spokes, and these spokes do have some weight. You said, how would you incorporate just one spoke into that formula? If you looked at one spoke, then you'd have to say, well, this is one spoke. Now you'd have to take that one spoke and break it into segments, figuring out what the mass of each little segment is in the spoke. And then each one has a different distance. For the tire around the edge, they're all the segments of the rubber are all the same distance away from the center R. For the spoke, that's not true. This would be like, R1. This one would be like R2. This one over here would be like R3 because each little chunk has a further distance. That complicates it quite a bit. That becomes much more complex. For that reason, you wouldn't be, you could do it. Computers usually do it. You put these equations in, type in certain parameters. A lot of the stuff that we do, if you go on to become an engineer, the computers are going to calculate this stuff for you. Not many people sit down and are doing calculus, just so you know. I mean, most people are working in teams. They're using technology and computers. They have to know all of this stuff because when you look at the computer programs, it has all references to all of this stuff. But if you don't understand it, you'd never have a shot. Just pointing out, most people aren't sitting out doing, getting out a piece of paper at their job and starting to do some difficult calculation, usually done by the computers. So, what I've described here, each little piece, a computer can handle that easily. And the distance it moves up each time is really, really tiny. It moved like a millimeter up and then a millimeter up, and it would make, 10,000 segments out of one spoke so that it had a really accurate determination for the rotational inertia of that one spoke provided to the whole wheel. And then it would move over to the next one. And it could probably do that whole calculation in 0.1 seconds. And it's correct, as long as the people programming it have put the correct formulas in. So these are little metal spheres. They say, assume that the spokes, I guess if you want to call these spokes, they usually call them thin rods, just using the language that you would find inside of a textbook. Thin rods, negligible mass. Why do they say negligible mass? Because of what I just said. If they didn't and you had to think about that, that becomes complex. It becomes the spoke problem that I just talked about. So at the first level, they're like, let's just, say that you don't have to worry about. They're so thin that they provide very little weight, but they're strong enough that you can attach these weights to the end. And this thing is going to be rotated. There's some axis of rotation like this. This would be like yikes. Oh no, what's happening to my marker? Don't do this to me now. Okay, I think it's working okay. What was I saying? Metal spheres, thin rods. What was I don't even remember what I was just writing over here. Thin rods, you're just going to negligible mass. Yeah, just going to rotate it. I don't know what I was about to write something. I can't remember. So, that's what I was going to write. Just noting that this is considered the axis of rotation. I'm just putting in a.r for it's just imagine that again. There's some central thing that you grab one of these metal spheres with your hand and boom, you give it a wing, and boom, and this thing just starts spinning like my wheel. and they're all spinning around this central point. The typical question is, what is the moment inertia of this object? Usually they would give you distances, and I'll do that in a minute. The distance from the center out to M1 is called R1. The distance from the center out to M2 is called R2. The distance from the center out to M3 is called R3. And the distance from the center out to the fourth one is, not surprisingly, called R4. They provide this nice symmetrical problem as the first one because R1 is equal to R2 is equal to R3 is equal to R4. They all have the same radius. Like on my tire, oops, I didn't mean to put it up there. Like on my tire, all of the chunks of rubber on the edge of the tire, they all have the same distance from the center of the tire. Okay, so how would I actually do this problem now? I'd have to give some numbers. Let's just say, M1 was 1 kilogram, because you have to have some numbers. Let's say M2 is 2 kilograms. Let's say M3 is 3 kilograms of metal stuck out there and 4 kilograms of metal stuck out here. So I just decided to stick with the 1, 2, 3, 4. So the heaviest metal ball is the one on the bottom with 4 kilograms. The lightest metal ball is on the left with 1 kilogram. Okay, so how would this work out? We would say that the total rotational inertia for this whole thing, how much does it resist a torque? Presumably someone's going to grab the end of this again and provide a torque. And the question usually is, determine the angular acceleration during the time that the torque is applied. But like I said, you can't determine the angular acceleration unless you know two things. How much torque is being applied, and what's the rotational inertia? So if they give a problem like this to you, and ultimately they just say, what's the angular acceleration? You would need to know as a student, I've got to actually calculate the rotational inertia first, because remember that or alpha, like I had written before, alpha, which by the way, I'll just write it now, torque over I. This is, might as well jot that down. This is Newton's second law for rotation. So A is like alpha, tau is the torque, that's like F, and capital I is like M. It's the resistance to being moved, or the inertia. Again, this is an analogy for F net, this is an analogy for A equals F over M, F net over M. So technically this should be like this. So if they asked you for the angular acceleration, again, you realize this is much more complicated. Like in a linear scenario, they just say, they give you the forces, 5 newtons of pulling to the right. Maybe there's 2 newtons of friction backwards. All right, 5 minus 2, net force is 3 newtons. Not a lot of work, not a lot of difficulty mentally to figure that out. Yet when a problem like this occurs, torque now is more involved, right? You'd have to reference some particular force that's being applied like this. There's a force being applied perpendicular. I don't know why my marker is doing that. You'd have to apply some force, like I drew in there to the left, and then you'd have to calculate the torque. You'd have to do F, this perpendicular force, times R. R is the distance from the center of this out to where F is being applied. Not really sure what's going on with my marker. So you'd have to calculate torque. Then you'd move on to step 2. Again, if their question was, what is the angular acceleration during the time the torque is applied, which is usually their question, then you'd have to move on to step 2, which is calculate the rotational inertia. It's like figuring out what M is, but not quite. That's what we'll do now. Then once you have both of them, you'd take one, divide it by the other, and you can say, okay, finally, I know what the angular acceleration is. That tells me how much rotational speed it should gain per second. And then they say, assuming that the torque is applied at constantly applied like a washing machine, it doesn't just provide a little bit of force and then let go. Is it's going into a spin cycle, washing machine for clothes. It's just a constant torque. Vroom, 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 vroom. That thing just keeps going faster and faster and faster. The motor is continually applying a torque. And the rotational speed keeps going up by some amount each second. And ultimately, you could work out what that was if you knew what alpha was, right? If you knew alpha was pi radians per second, then you know after 1 second, its rotational speed would be pi radians per second. After 2 seconds, it would be 2 pi radians per second of rotational speed. After 3 seconds, 3 pi radians per second. That assumes the acceleration was pi radians per second each second. But again, you don't actually get that numerical value until you use this Newton's second law. That's just a full global view of where this all goes. So this is a plug. I consider this plug and chug. You can try it yourself if you want. In fact, I'd encourage you to try it. Technically, there's 4 terms. I didn't give you the distance r yet. Let's just say it's 50 centimeters. Just know that 50 centimeters would have to be 0.5. It would have to be 0.5. You can't put it in centimeters. M always has to be kilograms. R always has to be meters. So R1, R2, R3, and that formula that I just wrote on the top, they're all the number 0.5. And then you just have to be careful with what are my masses. M1, look at the diagram typically. M2, look at the diagram, plug them in. You end up at a calculator and you're adding it all up and then you hit enter. Whatever number pops out, that's the total rotational inertia of this so-called system of objects. Give it a try. Again, you're trying with this right here. Always come back to your formula. The question, which is a good question always to ask, is what are the units? Just come back to the formula. The question is, what are the units for rotational inertia, presumably, right? So what would the formula suggest? Since I is m times r squared. Kilograms for m times meter squared. Yep. Since r is meters and it's squared, then it has to be kilograms times meters squared. Just an FYI, since a student just asked that in class. Those would technically be the units for for rotational inertia. Kilograms times meters squared. And again, knowing that you can just think of the formula to figure out what the units is a useful skill, useful awareness to have. So in fact, I'm going to say one other thing because I just realized I only got like 8 minutes left or something like that. How about let's just make it a full problem. I didn't do a good job drawing F. I should have done a better job drawing F. It kind of got all mucked up in here. Kind of lost in the mess. So I'm going to make it a full problem. I'm going to draw F right here. Let's assume that the applied force in magnitude is 20 newtons. So something over here on the end is going to grab it. That will be like my hand or something, just giving it the spin. 20 newtons of force. All right, so ultimately, why don't we do what I had suggested? What is the angular acceleration? Or do what I had described to you. So, because again, you might as well see the whole picture. The whole picture is that this would likely be, a question about the angular acceleration. So I have that written up on the top right. So A is F net over M. That's for the linear scenario. A is like alpha for angular acceleration. F net is like torque net. And then M is like I. It's Newton's second law. It's exactly the same. It's the same concept. The numerator is the force that causes the acceleration. The denominator is the resistance. It has to be motion, a motion quantity like A. It can't be proportional to the weight of something, right? It has to be inversely proportional to the weight of something because more weight means less motion. So A, being inversely proportional to M must be the same with alpha being inversely proportional to I. So utilize this to answer the final question. Because then at that point, You'd have I, the rotational inertia, which is up on the top left here. And then the torque, well, you probably remember torque is just R times F, right? Just jot that here. Torque is R times F perpendicular. And that's what would be provided on the top of this net torque. It's just one force. So it's like them saying there's a box on the floor. There's no friction. A person comes over and pushes it with 5 newtons of force. What's the net force? 5 newtons. There's no other forces. The ground, of course, up and the weight down cancel. So in this case, it's like assuming there's no other torques. There's just one torque. So the net torque would just be R times F perpendicular, which comes from the left side of this cross. So that would be it. I'd say try that. I'll probably provide something online for you guys to upload your work so you can get credit for it. At least it has given you a preview now of all the moving parts to this. I don't necessarily think that it's super hard. I just think it takes time. It's more time consuming. There's more parts that you have to figure out when you're given these kinds of problems. But once you get a little practice with it, I think most students become fairly comfortable with it. So again, I will make a spot for you. You can upload your work that shows the total rotational inertia work and calculation. And then part B, in the bottom left, what is the angular acceleration it experiences, assuming that 20 newtons of force is applied in the downward direction right at the end of this left end of this cross as a torque. How about at home, guys? Do you have any questions at home? Any questions? Kyle, William, Catherine, Matt, Julian. Any questions? Okay. I got 3 minutes left. I will at least just say I'd like to probably pick out a few textbook problems. Remember that that PDF is still online. I guess I could still, yeah, I guess I will. I'll download the same PDF that comes from the back of chapter 8. I'll repost it again. I mean, yes, I want you to upload this, so this is like a classwork thing. But I'll probably pick there's a section, I don't know if it's 8.5 or 8.4, that's all about rotational inertia. And I'm probably going to pick the first couple from a textbook just so you get a little extra practice doing this sort of thing, a rotational inertia problem. Maybe it'll involve torque. I hope so. Maybe I can find one that involves torque that's not super complicated, something that's a reachable goal that you can actually all do it. Maybe it involves what we did today plus a little torque, and so just look for that. I'll post that. That will be that'll be due tomorrow night. It's gonna be just a couple questions. But just remember, you got your exam. I really want you to do that. I mean, it's a good opportunity for you to really understand your exam. The reality is, for a lot of students, for most of the years of students, they don't really necessarily, some do, but a lot of students don't look at their exam. They just look at the score and then it gets shoved in their bag. They don't bother looking at it unless it's like, is there a reward for it? Do I get like candy, or like, do I get like my son says, do I get a reward? Then I'll think about it. And if you're like, no, I'm not doing it then. Well, at some point you get over that and realize the reward is your education. That is the reward. Learning and understanding is the reward. It will pay you every day for the rest of your life right through retirement. And you'll potentially have a great retirement because of it. The lifelong reward. So it's a good opportunity because I make it an assignment again for you to really look at your free response questions and really look at it, really understand it. Just a reminder, I hope that you guys can go right into the comments in that and just type in whatever you think, 35 out of 40 or whatever it is. I don't remember. But I'd like to just see that right in the comment section. It's a private thing. When you type a comment, it's just straight to me. So please, once you know your overall score, just put it right in the comments so I can see it. All right, guys. Have a wonderful day. see you on, just trying to think about the day, Thursday, I guess. See you on Thursday. I hope I see you on Thursday. Hope I feel well enough. Have a good day, guys. What's that? J&J. It's what I would recommend, but everybody has different preferences because there does seem to be more protection for the new variants that are circulating in the J&J, where the Moderna and Pfizer were actually manufactured before the variants really came out. So I don't think it's as sure about how much protection they provide. So that's why I'm getting J&J. Oh, any of them are great. Any of them are great. Yeah. So I don't want to make anybody think they made the wrong choice. They're all good. They're all good. They're all good choices. Actually, you guys weren't allowed to. I thought that. So how old would he be? So if you're 16 or older, you can get the shot. Oh, for some reason I thought it was older than that. I thought it was an 18-year-old or something like that. That's good. I didn't realize that. So that means some percentage of our students will potentially be vaccinated. Yeah, good.
I was wondering, can I please use the extra credit points?
Bye, Dorothy. Bye-bye.
Can I please use the extra credit points from the last test on the multiple choice?